So, hello friends, welcome to SCIENtwork. I'm your host Shashank, and today we'll be speaking on
India's Chandrayaan 3 mission.
The Chandrayaan 3 mission.
For the unknown, Chandrayaan 3 is a follow-up mission of a partially successful Chandrayaan 2, Indian Space Research Organization's flagship lunar rover mission to successfully demonstrate soft landing on the moon. Note that soft landing here means safe landing. Chandrayaan 3's predecessor Chandrayaan 2 was the rover plus orbiter mission and was ISRO's first attempt to demonstrate soft landing capabilities on the moon. Though the orbiter was successfully placed in the lunar orbit, but unfortunately due to a software glitch, ISRO lost communication with its lander at an altitude of just 400 meters from the moon. Chandrayaan 3 is ISRO's attempt to successfully carry out a soft landing near the moon's south pole and deploy the rover for scientific exploration for a period of one lunar day. Till date, only 3 countries have been able to demonstrate soft landing capabilities on the moon. Though Chandrayaan 3 and its predecessor Chandrayaan 2 share the same objectives, yet they have key architectural differences. Chandrayaan 2 was the lander plus rover plus orbiter mission, whereas Chandrayaan 3 is a lander plus rover plus propulsion module mission. Overall, the only difference between Chandrayaan 3 and Chandrayaan 2 is orbiter of Chandrayaan 2 being replaced by the propulsion module of Chandrayaan 3. The difference between these two lies in the number of scientific payloads, meaning instruments. The orbiter of Chandrayaan 2 has 8 scientific payloads, whereas the propulsion module of Chandrayaan 3 has just 1 scientific payload. As I mentioned earlier that Chandrayaan 3 is a combination of 3 modules, now we would be seeing their working in detail. Propulsion module carries the lander and the rover module until 100 km altitude from the lunar surface, from where the lander separates out and heads to the moon, and the propulsion module continues to revolve in the same orbit, acting as a communication relay satellite between the lander and the Earth. Once the lander successfully lands, it establishes communication with ISDN, Indian Deep Space Network, and then deploys the rover to carry out exploration near the vicinity of the lander. Please note that the range of rover is 500 meters from the lander, meaning the rover can move a maximum of 500 meters from the lander. In case the rover moves beyond 500 meters from the lander, then
Connection lost.
3, 2, 1.
Wait. Before we start, it's necessary to be aware of a few important terms like orbital velocity, escape velocity, apogee, and perigee. Now coming to apogee and perigee, they are terms related to an elliptical orbit. Basically, any ellipse has 2 foci. If we assume the planet to be on this foci, then the nearest point to the planet would be its perigee and the farthest point its apogee. Now coming to orbital velocity and escape velocity, they are terms specific to a planet and a circular orbit combination. Orbital velocity is the specific velocity to be maintained by a satellite to stay in a particular circular orbit. On the other hand, the minimum speed required for the satellite to break free from the planet's gravitational grasp and exit its orbit is called its escape velocity. Chandrayaan 3 uses the orbit-raising maneuver technique to move to higher altitudes in lesser fuel. Basically, what happens here is, while revolving in an orbit, firing the satellite just at its perigee allows the satellite to increase its apogee and velocity without significantly changing its perigee. Repeating this step a certain number of times increases the velocity of the satellite to its escape velocity, allowing it to escape the planet's gravitational pull in significantly lesser fuel compared to direct firing from the planet. Chandrayaan 3 also uses the orbit lowering maneuver technique to move from higher orbits to the moon. This technique is exactly opposite from the orbit raising maneuver technique. What happens here is deaccelerating the satellite, that is by slowing down its speed by backfiring the satellite at the perigee, kicks the satellite from higher orbits to lower orbits. So summing up everything, Chandrayaan 3 uses a combination of orbit raising maneuver and orbit lowering maneuver to reach the moon. So starting from the beginning, the entire Chandrayaan 3 module is carried to the near-Earth orbit via ISRO's launch vehicle LMV-3. Once inserted in the near-Earth orbit, the module performs 5 orbit-raising maneuvers to attain the required escape velocity. And once the escape velocity is attained, the module enters the Earth-to-Moon transfer orbit and heads towards the Moon. Once the module gets captured in the Moon's orbit, it performs 5 orbit-lowering maneuvers to shift to a 100 km radius orbit from the Moon. Now finally, the lander separates from the propulsion module and heads towards the Moon, whereas the propulsion module continues to revolve in the same orbit, behaving as a communication relay satellite. Since this is most like an engineering capabilities demonstration, so the mission has just basic payloads and it isn't really expected to collect a lot of new or groundbreaking scientific data. Coming to the lander payloads, we have ILSA payload which measures seismic activity, meaning moonquakes just like earthquakes on the moon. This would provide a deeper understanding of its internal structure. This information gathered from ILSA can help in studying the moon's evolution and shed light on one of the most popular theories regarding moon's origin, giant impact hypothesis, which suggests that once a Mars-sized celestial body collided with the early Earth and the debris from this collision eventually formed the moon. Seismic data revealed from the moon can reveal the moon's layers and potential similarities or differences with the Earth. Now coming to the Ramba payload, it helps in studying the moon's atmosphere and ionosphere. Though we know that the moon does not possess any atmosphere because of its low gravity, but the first convincing evidence for an ionosphere around the moon came from the Soviets' probe Luna 19 and 22. While circling the moon at a close range, the orbiter sensed a layer of charged gas tens of kilometers above the lunar surface, containing as many as 1000 electrons per cubic centimeter. Why an airless moon possessed such an ionosphere, no one knew. The initial answer proposed to this was lunar dust, meaning because of the sun's UV rays hitting the lunar dust and hence creating charged particles. But it wasn't that convincing. Ramba payload could possibly help answer this. Coming to the LRA payload, it helps in laser ranging studies, measuring the distance between the Earth and the Moon, using lasers fired from the Earth and reflected back to the Moon. Now coming to the CHASE payload, it studies how heat moves across the Moon's surface. By studying heat flow from the interior to the surface, scientists can infer whether the Moon has a solid or a liquid core. But what is its significance after all? Let's understand that presence of a liquid core means a global magnetic field around the planet. Since our Earth has a liquid core, so it has a global magnetic field. This magnetic field is what protects us from solar storms. Now, since Moon does not have a global magnetic field, so it was assumed that it had a solid core. But various missions and researchers conducted on the Moon showed many magnetic anomalies, which suggests that the Moon once possibly had a liquid core which later on solidified. This theory is widely known as the lunar dynamo theory. Data gathered from CHASE payload could give new insights to this theory. Now coming to the rover payloads, the rover carries APXS and LIFS payload, which together aim to study the chemical composition of the lunar soil. This knowledge can help us understand the Moon's geological evolution and potentially provide clues about its past and environmental conditions. So summarizing everything, we initially saw why Chandrayaan 3, where we presented it as a successor of Chandrayaan 2. Then we saw the architectural differences between Chandrayaan 3 and Chandrayaan 2. Then we saw the architecture of Chandrayaan 3, where we explored Chandrayaan 3's modules in detail. Then we saw Chandrayaan 3's journey to the Moon, where we explored the basics of orbit maneuvers. Then finally we talked about Chandrayaan 3's scientific payloads and what do we expect from them. Thanks a lot everyone for watching our video, and if you like our content, please like, share and subscribe our channel SCIENtwork.